So two of the code names that Mike threw out were Longhorn, which you've heard about all week. The other one was Springboard. So let me give you a little bit of an inside scoop where those names came from. A lot of us in Windows are skiers, and as you know, Redmond, or you may know, Redmond is a hop, skip, and a jump away from British Columbia, which has North America's best ski field, Whistler and Blackcomb. Well, for those of you not aware, when Windows Server 2003 was being built, it was known as Whistler Server, and when the client, Windows XP, was being built, it was known as Whistler Client for a long, long time, until we finally got a name for them. So Longhorn is a meeting house at the very bottom of Whistler and Blackcomb. Okay, it's not a meeting house, it's a big pub. So that's where the Longhorn name came from. And Springboard is actually the last ski run off the mountain to Longhorn. So now you know. I don't know why anyone clapped about that one. All right, so let's move into the technical aspects of this presentation. I call this a fireside chat because I tend to have really ridiculous conversations with people that just don't care, like my family, about the hostilities on the internet and what it takes to build secure software. And so I've had this conversation. I actually treat this literally as a conversation with many people, so they understand the way that the threats have changed. So if you look at some of the trends that are occurring today, and just sort of freeze this image in your mind, but we're an increasingly more mobile workforce. And just look at some of these figures. 60-odd million mobile workers in the US today. That's just the US. 60 or so million handheld computers are going to be sold this year, give or take. The boundaries are really changing about what we determine is the corporate environment. We always sort of knew what the physical constructs were that made up the company. And we also used to understand where the network stopped. The network, or the trusted components of the network, stopped at the firewalls. Well, that has all completely changed. There's no notion of these solid boundaries anymore. I mean, how many of you have a laptop or a mobile device that has Wi-Fi support? I'm sure all of you have. Bluetooth support. I mean, we all have these devices capable of mobile connectivity. And so what's happened is that the boundaries to the enterprise have changed. They're very porous. The other example I like to bring up, which is something that Mike alluded to, is this notion of devices sort of crossing the firewall every single day. These mobile devices that you have at home, these laptops, they run at home, they're connected to the internet, they may get infected, you shut them down, you bring them past the firewall, and you open up the network, you open up the laptop or the mobile device on the network, and you've now potentially compromised the network. And so these firewalls that we have in place are being transgressed every single day. This brings a whole new class of threats that frankly didn't exist 4, 5, 6 years ago, which are very serious threats today. And ultimately what I'd like to say is that the threats have changed. Software that we built 10 years ago, and by we I mean the industry, may not be secure enough. There are protocols that were designed many years ago that may not be good enough today. They were fine 10 years ago when everybody loved everybody else, but that's not the situation today. You may live in the nicest part of town, have a big flash house in the nicest, safest part of town, but the moment you plug that network cable in the wall, you are in the seediest neighborhood on the planet. I'm deadly serious. You think about it. There are some really rotten people out there. I mean, do you wonder why attacks occur? The threats have changed, and we need to realize that the practices that we had from 10 years ago for designing, building, testing, and documenting software really isn't good enough today because the threats have changed dramatically. And the reason why I'm actually wearing my Microsoft ID is to show one thing, which of course no one's going to be able to see from here. But there's a smart card on the back of my ID. Now, the reason why there's a smart card on the back of that is that the Microsoft corporate network is under constant password guessing attacks from outside the organization. And frankly, passwords are an atrocious authentication scheme. They were fine 10 years ago, but they're just not okay today for very sensitive environments. And so the reason why everyone is armed with a smart card at Microsoft is not so we could exercise the Windows 2000 or the Windows Server 2003 PKI infrastructure, which, by the way, held up very well. But the reason why we did it was if you want to access the Microsoft corporate network remotely, you must use a smart card. You can't access the network at all except using a smart card. And the reason we did that wasn't just to make the PKI guys happy. It was because the threats have changed. And we had to do it. So let me show you a very quick demo. It's a good old buffer overrun demo. Actually, I'm amazed my machine didn't go to sleep. I was expecting it to go to sleep. All right, so this, let me give a little bit of a story to this demo. This is actually part of a demo that is given by the Office team. This is actually stolen from the Office guys. Sorry, borrowed from the Office guys. They have this process, which a lot of product groups, and we have a similar process as well within Windows, where if you join the product group, you go to boot camp training, security boot camp training. And this presentation is also given to interns as well, that we have from university who are interning with the different product groups. And the reason why we give this presentation is to show that buffer overruns are very, very real and how they actually work. And so this is put together by the Office guys. There's some code here, and it's a classic sort of interview question for an intern or an interview candidate, is how do you take a sentence, reverse all the words in that sentence? It's a classic interview question. And there's a security bug in this code as well. And of course, all of you know exactly where the security bug is. Or at least I hope you know where the security bug is. Well, the bug actually is pretty straightforward. And my mouse isn't working. Oh dear. No mouse. Oh, here we go. Thank you. So the bug in this code is pretty straightforward. There's a buffer overrun in the code, hence buffer overrun exercise. This is actually part of, there's an ActiveX control in here just to show the layouts of the stack. I'm not going to go into great detail right now about what the stack looks like. I'll show this a little bit later. But there's some critical things that are held on the stack. Stack is just the region of memory that's used internally. But when you call functions, the stack grows down in low memory as functions get called. And some sensitive data is held on the stack. One of the most sensitive elements on the stack is actually the return address. Where does the function return to when the function actually returns? In other words, who called me and what instruction do I need to continue execution at? If you actually look at the code further up, you'll see that some variables like SZWork is a buffer that's 32 characters in size, and so on. And so SZWork is actually here in memory, this block of memory here. And you'll see here it says type something here, so I can hello Blake. I better put Paige in there as soon as I have a new daughter. And if I reverse that, you'll see down the bottom that will say Paige and Blake hello down here. And you'll see that the data on the stack has been changed to reflect this new data. Well, as a bad guy, I'm not going to type in hello Paige and Blake. I'm going to type in something even nastier that will actually clobber this return address on the stack. So when the function returns, it actually calls my code instead. Now, in this case, I've got to be perfectly frank with you. It's a kind of a contrived example. All I'm going to do is call load library. That's all. But you imagine, I'm calling load library. I could be calling anything I wanted. But I'm just going to call load library. And just to save me a little bit of time, I have the string, because I'm not typing that in by hand, already in here. And so if you look now, you'll see where the data has changed to red. And this buffer is actually bigger than the size, is bigger than 32 characters. But most importantly, I have clobbered this, the return address, with a value, which actually is some code that's actually held in in the buffer that I provided, this series of hex digits here. And now if I try to reverse that, so let me just explain. This is not some script that's happening. I'm actually calling load library, which is calling some function, some DLL on the disk, and actually executing it. And that was just in a small number of bytes of malicious payload. It could have been much, much worse than this. I'm just calling load library. I could be calling load library on something, on some other function, on some other library that calls some other function later on to do something even nasty like formatting hard drives, adding the guest users to the admin account. And of course, I can easily add the guest account to the admin account because everyone runs as admin, and the admin can add the guest account to the admin group. So that's just a real simple example of a silly buffer overrun. But the whole point is, it's amazing how many people we talk to, and in fact, how many people we interview who don't think buffer overruns are actually real. They actually think it's a figment of someone's deranged imagination, and it's just to keep our security guys in business. That ain't the case. So anyway, back to the demo. Sorry, back to the presentation. So ultimately, software has to adapt. In fact, we as an industry need to adapt to these rising threats. There are new threats on the horizon that we may not know about yet, and we need to adapt to all of those threats. But when I talk about threats, I don't just mean just pure security threats. I also mean competitive threats. In the good old days of 16-bit Windows, we all embraced 16-bit Windows because we recognized it would give us a competitive advantage. By we, I mean the industry. It would give us a competitive advantage over our other competitors. So if you were building a spreadsheet program, then you may have a competitive advantage over somebody else, assuming Windows did well. The same with 32-bit Windows. People adopted 32-bit Windows for software development for a competitive advantage. Same with building stuff that was connected to the internet. Same with XML web services. However, we now must adapt to a less trusting environment. Now here is the problem. You either adapt and gain a competitive advantage because of that hostile environment, or your competitors will. It's a simple fact of life. These hostilities are so serious that all our software must adapt so that we end up getting a competitive advantage. And frankly, this is kind of a bit of a cynical comment, but any software from the nice end of town will not survive long in the slums of the internet. It will get whacked. And in fact, security is a huge thing. And in fact, I'll go as far as to say that security is the current big thing across the internet. And unfortunately, the skills required to design, develop, test, and document secure software are severely lacking across this industry. Ignorance isn't bliss. Do not think for one moment that you can stick your head in the sand and say, well, the problems, there's no problems, there's no security problems, and expect them to go away. They won't go away. The problem with ignorance is that ignorance is not bliss for you. Because you may not know what the problems are, or you may not care to know what the problems are. Unfortunately, the bad guys out there do. And unfortunately, all it takes is one bad guy. That's all it takes. Just one bad guy to take you out. So I'm going to sort of spin this whole thing around. I'm not going to try to scare you into saying that security is interesting and security is important. I think security can be used as a competitive advantage against your competitors. By you building more secure software than your competitor, I think, will help you sell software. Now, I mentioned before that all it takes is one bad guy. And it's absolutely true. As people who are building software, the software developers are in a very, very difficult situation. And there's this little thing that I like to call the attacker's advantage and the defender's dilemma, which is, so principle number one is the defender must defend all points. Think of a citadel, or think of a city for a moment that's got a walled city. The defenders must defend that city. They must defend every single point and entry point into that city. Whereas the bad guys just need to look for one weak point. The really downside is the defenders must be constantly vigilant. They must be always looking for the bad guys and seeing if there's any vulnerabilities. The bad guys can take as long as they want to find that one bit of vulnerability, that one weak point, and then strike at will. So they can wait until you're not looking and then strike. And finally, and this is probably the hardest point, and this is what I think makes building secure software so hard, is that the defender can only defend against what he or she knows about. We can only build software based on the threats that we understand today. Well, the problem is the threats are evolving. And so when you freeze your software in time and you ship it to customers, at that point, it encompasses all the security expertise, or a subset of the security expertise that is known on that, up to that point in time. Whereas the bad guys will continue to do research and find issues. And we can't defend against those very easily. And I have this little saying, which is ultimately build it and the attackers will come. I can promise you that. As the moment people hook up that machine and they plug it in the wall, the bad guys are there. And there's millions of them, and they could be anywhere on the planet, and you don't know where they're coming from. So building software for people is actually fairly difficult. It's a fairly difficult thing to do. Mainly because you've got this software and it's being tugged in every single direction. And a lot of these are conflicting views. So you have to build secure software. You have to honor privacy. You have to honor reliability. It has to be compatible. Frankly, compatibility is one of the biggest killers of security. There's protocols that we want to deprecate. but you can't because they're being used by everybody. I mean, TCP/IP version 4 is a good example. It was never designed with security in mind. Never. It was designed in a day, and some would argue it was designed in a day, when everybody loved everybody else, and IP was never used to attack people. And it was never designed with any authentication, with any authorization, any kind of integrity checking, any kind of secrecy. It was not designed with that in mind. And so we have to run on these networking protocols. And it's the same with authentication protocols. There's also features that you may want to pull out of products that you can't because they're being used by absolutely everyone on the planet. It has to be accessible. It has to be used by people with limited visibility, for example, or limited use of their limbs. It has to be usable. You could build something that's really, really secure, but no one can use it. You're not going to sell many of those. And finally, it has to be doable. You've got to meet some kind of schedule. It's going to cost you money to make it. And frankly, the skill sets are required. So when you're building software, you have to take into consideration all of these things, and many more. So one thing that we're doing at Microsoft, and this is the whole point of trustworthy computing, is there is more emphasis on security, privacy, and reliability. And frankly, that may be to the detriment of some other aspects of this spectrum of building secure software. So let's look at the software pendulum, or the software security pendulum, sort of where we were. So if you look at so something that Mike alluded to is historically software has always been very convenient, very easy to use, which is great. And then the other side of the house, and some would argue that you don't have to have a very secure system, or a secure system does not necessarily mean a less usable system, but there is certainly a relationship between the two. And so historically we built software, and I'm in the industry, that was very easy to use. Unfortunately, that meant that you had a very large attack surface. Lots of features turned on by default. Things happened automatically. Event 1 happened, which triggered event B, and because that event was automatic, the user was never informed of it, but it was usable because the user didn't have to make some kind of decision as to determine whether that event should occur or not. Then there's internet time. A lot of software was built extremely rapidly. And we all know that if you build software extremely rapidly, chances are you can make mistakes. And so the other aspect of this building very usable software very quickly is the internet time. And finally, the big problem with the fact that you've got this large attack surface and things just happen means that things just work, which is great. But it also means that attacks may just work too. A good example is you see an email that says, "I love you." You think, "Oh, great, excellent." Double click. And the fact that the script engine just runs automatically is that automagic relationship between you double clicking on something and the script engine just running is great for usability, but not for security. And so one thing we've been spending a lot of time on is understanding where those links are and seeing if we can sever them in a usable way, which is actually pretty difficult. I believe where we are, or at least the vision of where the short-term vision of, say, about 6 months ago, where we want it to be, is the pendulum just completely swung the other way. So reducing the attack surface dramatically, which I'm still in favor of. The downside of reducing attack surface is that stuff just doesn't work anymore. Some of the top support calls for IIS-6 are how to make stuff work, because the feature's not turned on by default. Put it this way, I'd rather take some phone calls from people saying, "I can't get something to work, how do I get it to work?" rather than how do I recover from a compromise. It is often harder to use. There's also this thing I call knee-jerk security. Throw up a dialog box. Just ask the user a question. You know what? Most users don't understand half the dialog boxes we throw up. A good example is there was a bug, a dialog box in IE, where if you added a root certificate, this dialog box will pop up, which basically had the words like, "This is the most important security decision you'll probably make this week. SHA-1 hash, MD5 hash, yes or no?" Sure. I remember asking my wife, "So what do you think this dialogue means?" And she immediately reached for the Tylenol. But she said, "Which button do I press to get my job done?" I said, "You hit yes." "Okay, I'm going to hit yes." And unfortunately, she now trusts any certificate issued by, Charlie's Certificate Issuing Corporation. whoever Charlie is. So this knee-jerk reaction of just throwing UI is actually a detriment, because eventually users will see all these stupid security dialogues popping up, and eventually they'll just say, yes, just get out of my face, yes, yes, security be damned, yes. I've seen too many of these dialogues. So this knee-jerk security leads to dialogues. And frankly, it can be slower to market. If you spend a lot more time on this work, it can be slower to market. It is a detriment. Where I believe we should be, and we're now toning back some of the work that we've done to make it more usable, is having a smaller attack surface. We need to reduce the attack surface anyway, but not making it so small that the products are just unusable. Security and privacy are first-class features. They're just like the performance of the product. They're just like the normal features that will be built into the product. They're a first-class citizen. And the reason why you do that is things that are first-class citizens on the schedule are in the schedule. Features that are first-class citizens are taken into consideration actually when you're planning the product. If you don't plan for security and you don't plan for privacy, you won't get it right and you will slip your schedules. I guarantee it. Because actually, security problems are probably the hardest of all the bugs to fix, because I can guarantee that the fix will cause regressions. I can almost guarantee it. And fewer security problems. It's a hard problem to solve. I'm not making that as an excuse, but it is a hard problem to solve. So making it as transparent as possible and make it configurable where it's appropriate. And that will vary by product. So Windows XP and Longhorn clients will have different types of security problems than, say, a server. And ultimately is making it securely usable. Making it usable enough but still secure. So the call to action, which is really a kind of a repeat of Mike's call to action, so I'm not going to spend much time on it, which is, in fact, I want to just point just one bullet point out. I think it's the most important of the lot. And that is the first one. And that is a process. So something I say to people many, many, many times a day is you can't design stuff, build stuff, test stuff, code stuff, document stuff, look for security bugs and ship. Well, you can do it, but don't expect to ship a secure product. And heaven forbid you design, code, test, document, ship, and then look for security bugs. That is not how you do it. The way you build secure products is by having an end-to-end process that has built-in time for design and a process that fosters building and designing secure software, building secure software, good test plans, a good testing team, good documentation, discipline, and policy, and good patch management, building things like threat modeling, security pushes, security audit, checks and tools and checklists, as Mike alluded to. You have to have that process. And we're building that into the way we develop software at Microsoft. And something you should be aware of, it adds about 15% to the time. It adds about 15% to the schedule. You may think, oh, that's just too much. I can't handle that 15%. We found that if you don't do that, your schedule blows out by about 30%. So I think it'd be much better to bite the bullet up front and build it into the schedule and have it as part of the process. And in fact, the rest of the symposium is all about that call to action, which is implementing best practices, a good process, and then we'll show you some solutions at the end of the session. All right, so with that, I'm going to move straight on into security practice. And what better way of doing it than starting off with a code defect? So I know this is small code, and I apologize for those guys at the back. But would anyone care to guess what's wrong with this code? By the way, I'll give you a little hint. This is the code that was found in DCOM by some gentlemen in Poland, last stage of delirium, that led to the blaster worm. Can anyone tell me what the defect is? So there's a function called at the very top there called remote activation, which is about 1,000 instructions away from port 135. So in other words, it's hanging off the internet, ultimately. This then calls down to a function called getServerPath, which then calls down to another function, getMachineName. Well, the very last two lines of the code there are a while loop that doesn't stop copying until it bumps into a backslash. Well, what happens if the backslash occurs after the size of the destination buffer? You've got a buffer overrun. The core error with that code is copying untrusted data. Some data came off port 135 and you blindly copied it into some buffer. And if you look at the construct that's used there, while something does not equal some character, then just keep copying. And it's constrained by the source data, which came from the bad guy. It's not constrained by the destination size. That was the defect. But the ultimate lesson here is copying untrusted data. If that data were trusted, then we wouldn't really have a problem here. The code is defective, but it may not be a security vulnerability if the data were always trusted. But in this case, it's hanging off port 135. It's not trusted. And in fact, I contend that there are two major types of defect. And it sounds like a very flippant comment, but I'm actually deadly serious. Number one is input trust issues. Number two is everything else. My view, and this is my own personal opinion, but if we as the industry can fix that first bucket, the other class of bugs kind of become uninteresting. The first ones are the very, very serious bugs. For example, buffer overrun. Why do buffer overruns occur? Because you expect this and get this. You expected the data to be this because you trusted the data was well formed, and it wasn't. You got this instead. Why do SQL injection attacks occur? Because you expect someone's name as part of a SQL statement, but someone gives you something that's a little bit more interesting. And we'll give you a demonstration later on of a SQL injection attack and a tool that even helps build SQL injection attacks. Then cross-site scripting bugs. Once again, you expect something on a query string, and the bad guy, oh, he gives you something on the query string, all right, but it's not what you expected. It wasn't someone's name. It was some JavaScript and some HTML text instead, which causes client machines to be compromised. So all these are just input trust issues. Another example, integer arithmetic attacks. I'll give you an example of this shortly. You expect some numbers to be in a certain range, and you expect the numbers to always be in that range because the RTF, the RFC says, you know, this data will be in this range. Well, the bad guys don't give you data in that range. They give you data that's in a different range. And so you add these numbers together, or you perform some kind of arithmetic on these numbers, and you get a very interesting situation. And so adding numbers together can cause serious security problems. Like I said, I'll give you an example of this shortly. So let's talk real quickly about buffer overruns. I'll give you a quick example of what they are. I'll explain a little bit more detail, but I don't want to go into too much depth because I assume people kind of know what they are. External data is larger than the destination that you're copying the data into. And ultimately overflowing the destination buffer tramples on some sensitive in-memory construct that determines execution flow. If you think for a moment, that's exactly what the attacker wants to do. The attacker always wants to change the execution flow from what the normal execution flow is to an execution flow determined by the attacker. That's the ultimate goal of a buffer overrun. And the destination that the attacker wants the flow to go to is usually in some data provided by the attacker, which is the code that adds the guest account to the admin group or provides a reverse shell, those kinds of things. C and C++ code are by far the most common victims of buffer overrun, primarily because you're working so closely to the metal. You've got to realize, you know, C was designed as a replacement for assembly language. That's what it was for. Yeah, we use the language to build everything. But because you have such low-level access to such low-level constructs, which, by the way, are the reasons why people choose those languages, because they do allow you access to these low-level constructs. And so, because you have access to these constructs, they can be dangerous in face of untrusted data that is not verified. But the ultimate cause of these issues is trusting input. That's all it is. The fact that you trusted something was well formed and you were wrong. That's what causes these problems. Real quick example. By far the most simplistic example. Some function called copy stuff takes some data and copies it into a buffer. And if the data coming in is bigger than the size of the destination, then the call to stir copy will overflow the buffer. And unfortunately, after that buffer is some sensitive information on the stack. And at that point, you are owned. The box is no longer yours. Someone else owns it. How common are buffer overruns? So we were really surprised by this. We actually thought I'd go and spend quite a bit of time analyzing bulletins that have been issued this calendar year that have been issued by vendors to see how common they were. It turns out it doesn't matter who the vendor is, whether you're Microsoft, whether you're Linux, whether you're Unix, whether you're Oracle, whether you're Apple, it doesn't matter who you are. Approximately 25 to 30% of the bulletins being issued today are buffer overruns. This is not 5 years ago. This is today. It's about 30%, give or take. So why are they so prevalent? There's a lot of C and C++ code out there. And you know what? There's even more code being added on a daily basis. C and C++ are not going away. There's lots of legacy code out there that was never designed to run in a hostile environment. And all of a sudden we're hooking these machines up to the internet that were never designed to run in an unprotected environment. And all of a sudden they are. As I mentioned before, C and C++ give you access to these constructs that allow you to change the execution flow. One of my favorite examples is a vtable in a C++ class. It's just a series of function pointers. If you can whack one of those, then if I can overwrite that with a value that I determine, then I can change the execution flow when you call that virtual method. So it doesn't call your normal code, it calls my code that defaces your website. And the other interesting point is that there is these constantly evolving threats. There are new types of vulnerability that we don't even know about, or we don't know about yet. For all we know, 2 years from now, there'll be a whole new class of buffer overrun attack types that we don't even know about yet. Good old examples, the classic stack-based attack. That was always seen as the easiest, in fact, the only real attack that you could pull off with any ease, where you overran the buffer when a function was executing, overran the return address on the stack, so when the function returns, it returns to the bad guy's code. So then conventional wisdom at that point, and by the way, I never subscribed to this conventional wisdom one little bit, was, well, just don't have the data on the stack, move it on the heap. My contention is if you've got a bug, you fix the code. Don't just go blindly moving it on the heap. Well, now we know that heap-based buffer overruns are absolutely exploitable. Absolutely exploitable. Now, the reason why they are so exploitable is a lot of people thought, well, you know what, they're not really that exploitable. Yes, denial of service, my app AVs or my app core dumps, but it's not really that much of an issue. Then there was a presentation about probably 18 months, 2 years ago now by Halvar Flake at one of the Black Hat conferences, which was how to exploit heap-based buffer overruns. So all of a sudden, the level of knowledge in the community has raised substantially, where everyone can now refer to this paper and say, oh, that's interesting, so that's how you whack apps that have heap-based buffer overruns. Now everybody knows how to exploit heap-based buffer overruns. They are not rocket science. Then there's these things called format string attacks. I'm not going to give you an example of this, but ultimately it's using sprintf and such with %s's that are essentially the same as a stir copy. One byte buffer overruns, where your buffer overrun is 1 byte off. They're exploitable, or a quantity of them are exploitable. And there's a very famous bug that was fixed probably about 3 years ago now in WUFTPD in their globbing function that was an off by 1 buffer overrun. Now there's integer overflow attacks, or integer arithmetic attacks, as some people like to call them. I'll give you an example of this shortly, where adding numbers leads to buffer overruns. What's next? We don't know. But I can guarantee you one thing right now. There are people who are thinking about it. And we're thinking about it too. But there are a lot of people thinking about this. And it's important that we code in such a way that it's defensive, just in case these new vulnerabilities are found. And I say once again, the big problem is developers don't check their input. Now the reason why I say that last point is conventional wisdom is, you know, well don't write in C++, write in and just insert your favorite language of choice. It just drives me mad. No, you can't do that. You can't just say, you know, I never trust input, therefore I will write in C#. You still have to think about the input. You can't disengage your brain. Certain classes of bugs kind of become harder to pull off, like buffer overruns and such in a managed environment, but you still have SQL injection attacks. You still have cross-site scripting attacks. You can't disengage your brain. So let me go through the integer arithmetic stuff. So people, you know, often said, well, rather than me having this buffer overrun, what I'll do is I'll check that the data coming in is of an appropriate size, and then I'll do my memory allocation, I'll do my copy based on the calculation, and if the buffers are too big, then I will return from the function because the buffers are too big, and I'm not going to copy them. So here's an example of that code. We have a buffer that's 256 bytes in size. We're saying if the length of the two source buffers, when added together, is bigger than 256, then go away because you've given us the data that's too big. And then finally, we copy these two buffers into the destination buffer. So what's wrong with the code? So there's two interesting points. One is negative. Actually, in this case, it's not. The values coming in are both size t's, which are unsigned values. So a -1 will be treated as 4 gigs, essentially. Okay, someone got it. What happens if len1 is this really big number and len2 is this kind of smaller number? If you add the two together, you get 256. And so you add these two numbers together. If len1 plus len2 is greater than 256, then go away. Well, it passes that check. And then the next line tries to copy almost 4 gigs into a 256 byte buffer. Now, in this case, all you're going to do is AV. But there are many of these kinds of exploits that are completely exploitable. Sorry, these constructs that are completely exploitable. And you should be very, very careful about the calculations you perform when calculating a buffer size to be used in a memory allocation. Because you can often call malloc with the sum of these two functions, the sum of these two values, ends up allocating a much smaller buffer than you expected. And then you end up copying that much data into the buffer, and you overflow the buffer. So simple arithmetic can cause security bugs. What's really interesting about these is these were very, very rare. These were extremely rare 2 and 3 years ago. Now they're very common. And I've given you just some examples here, and believe me, this is by no means exhaustive. What's really interesting about one of them is one that's in the middle, is the Microsoft JScript integer overflow attack. If I had told you about this bug 2 years ago, or I had told the security community about 2 years ago about this bug, I would have been laughed off the stage. This was an integer overflow attack that led to a heap-based buffer overrun that was exploitable. 2 or 3 years ago, people would have thought you were on bad medication to make that assertion. Yet today, we now understand those to be exploitable. This is why I say the threats are changing. People are learning more about this stuff. So some of the remedies. There's remedies and there's mitigations. Remedies kind of fix the problem. Mitigations help make the problem less severe. I'm going to focus primarily on the remedies. First one is training. I've already said this. What you don't know about security will bite you on the backside because you may not know about it, but the bad guys do. And if your software is hooked up to the internet, the bad guys have access to that software. So training is absolutely paramount. You have to know this stuff, and it has to be an ongoing thing. One thing that we've now instigated at Microsoft, it starts this fiscal year, is that all new engineers go through security bootcamp training every year to give them all the new stuff because the training changed from last year. There's so much more that we've learned. A very increased focus, especially on code, or teaching people if they have code that has access to the network, runs by default, has an unauthenticated connection, and runs with elevated privileges. If you have 3 or more of those, then you need to learn more. You need to learn a lot more, and you need to spend much more time scrutinizing that code. Think for a moment, what makes a worm happen? The code is either extremely popular or running by default. The code is connected to the internet or opens up a port. Unauthenticated connections, and just to add a bit more zest, run as root or system or as admin. If you have 3 or 4 of those, 3 or more of those, you have the ingredients for a worm. That's why you need to spend so much more time on understanding issues if you have code that falls into that category. There's also some other places you can go, and in fact, on the handout of resources are these URLs as well. Enforcing less error-prone constructs. There are some function calls that are inherently dangerous. And I use the term dangerous in single quotes because they're not dangerous. They're only dangerous in the face of unvalidated, untrusted input. Dave Cutler, who was the chief architect of Windows NT when it came out, told me a couple of years ago, Howard, there's no such thing as dangerous functions, only dangerous developers. And he's right. I can write perfectly secure code that uses called stir copy and stir cat. Completely secure code. You can also write completely insecure code that uses stir n copy and stir n cat and these safer functions. They're not safe. They're only unsafe in the face of untrusted data. If you validate the data and do the right things to the data, with the exception of getS, which is just plain evil, that is a dangerous function. Then, you know, if you check the data coming in, it's safe. By the way, the reason why getS is dangerous is because you cannot check the data coming in. That's why it is dangerous. And as I mentioned before, just changing you know, over from the stir copy to stir n copy and so on doesn't make your code secure. People get the buffer size wrong. They do. And you know, well, I'm secure because I passed in the buffer size. Well, you got the calculation wrong. Well, I'm still secure because I passed in the buffer size. Well, you got to get the buffer size right as well. You can't just disengage your brain. So let me ask you a question. So when calling stir n copy and stir n cat, the buffer size at the end that you pass in, how many of you think you must accommodate for the trailing null in that calculation? Okay, how many of you don't think you accommodate for the trailing null? Okay, it's like 5 and 5, 50-50. The rest of you are like, what the hell's stir n copy? So let me explain something though. Every time I ask that question, it's always the same. It's 50-50. You know what that means? Half of you are wrong. But you want to know the really sad thing? I don't know which half it is. But one half of you is wrong. That's how buffer overruns happen. And I'm sure you're not stupid, but half of you is wrong. That's how buffer overruns happen. Anyway. Then there's, so we did introduce some functions, and I'll give you a quick look at some of these functions shortly. StirSafe, which was built during the Windows security push. Well, something that we've now proposed to the ANSI committees for C and C++ are safer replacements to the C runtime library as mandated by the ANSI committees. And we've now proposed that and it's been accepted. I'm not sure exactly what the status is, but it's on the track to being accepted as being a standard part of the C and C++ languages. If you're writing C code, then use the string, you know, the STL string class. It hides a lot of the complexities from you. And be very wary of arithmetic that can cause these problems. So I want to give you a very quick demo. I recognize how short I am on time. Helps if I get the right machine. Oh, I've been hacked. As you can see, IE is dead. I mean, it completely died. All right, here's some code. Real quick. There's 3 flavors in here. One is using good old stir copy, stir cat. The other one is using another example called StirSafe. It's using the stuff that was developed that is available today on MSDN. It's also available in Visual Studio .NET 2003. It's called StirSafe.h. And they're just more consistent ways of managing buffers. And the last bit of code down the bottom is using the new libraries that we proposed to the C and C++ committees, stirlen _s, stircopy _s as well. So if I just build this, let me clean it first. So compile the code. If I then run the code, so I'll step into Dangerable Robinson and I get myself a buffer overrun. Cool thing is, as soon as I step out of the buffer, as soon as I step out of the function, remember I talked about there's a thing called the GS flag that Mike talked about? Well, this detected that I'd actually compromised one of the buffers in this function, and so it just halts the process dead. And even in a debug build, it even tells you which buffer was compromised, which is actually pretty cool. So I'll break the application and I will comment out that call to Dangerable Robinson and rerun the code. And this time I'll step into the StirSafe code, which, like I say, is available today. And it barfs because, actually I'll do that again. It barfs because the buffers are not big enough, or the data coming in is too big. And you'll see, oh dear, what did I go and do that for? you'll see that the return, oh dear, let me do it once more, I'm sorry. The return value from stircat down the bottom is very easy to understand. The data area passed to a system call is too small. You've got a buffer overrun. It's fairly straightforward. Or the data's being passed in and it's too big. So I'll keep going. And now what I'll do is I'll step into the safe CRT, which is a little bit more hardcore. These guys just assert. And we'll throw a buffer too small error. And in the case of, this is a debug build. In the case of a free build, they will return a status message, and you can check that status message to make sure that the buffers were small enough. So just be aware that, so if you want to use these new functions today, StirSafe is available today on MSDN and Visual Studio.NET 2003. The safer CRT, I'm not sure exactly when that's planned. It's a little bit out of our control. All right, tool usage. I mentioned, in fact, Mike talks about tool usage as well. Tools are not a replacement for human beings. You can't take developers that know nothing about security, give them great checklists, give them great tools, and expect them to produce secure software. The best tool that we have is between our ears. There is no replacement for good engineers and good engineering. And so what you should have is good engineers that are educated, understand the issues, have a process in place that fosters allowing them to do the right thing and give them great tools as well. Building tools helps scale the problem, and it also helps enforce the policy that you have dictated to the corporation or to the company. Yeah, there are things you can add to the OS and to the compiler, which we'll talk about. In fact, Jason Garms will talk about this at 12:30 during lunch. So if you want to come back after lunch, Jason will be talking about some of these in more detail. It includes things like non-executable pages to prevent the payload from running when it gets into the OS. But there's no replacement for fixing the code. These are just mitigations. So I'll talk to you very briefly about the GS flag that's included with Visual C++. This, if you look at the first stack layout at the top here, this is what a normal stack looks like. And you've got buffers in lower memory, other variables. EBP and EIP are the return address. In other words, where does the function go to when it returns? And then the arguments on the stack. Well, if you compile with the GS flag in Visual C++ 2002, we'll insert a random value, a 32-bit value, just before the function return address. So if your buffer whacks that, when the function returns, it will halt the process. It's much better to have a dead process than have a process that is propagating a virus or a worm. I'm not going to say it's a great situation, but it's the lesser of two evils. We decided to take this one step further. The GS flag in Visual C++ 2002 would not have prevented code red. I'm not going to go into all the details right now, but it wouldn't because it didn't whack a return address. The code red virus actually whacked an exception handler on the stack. And so we went back to the Visual C++ guys and said, okay, how could we have prevented code red? Well, the first answer is, well, fix the code. But the next one is, how could we put a mitigation in place that would have prevented it? And so one of the first things that we did was recognize that these other variables after the buffers in higher memory can contain sensitive data, sensitive constructs that the bad guy will go after, like function pointers, like exception handlers, like vtables on the classes on the stack. So the first thing we did was swap these two around. So now, to whack one of these puppies on the stack, you have to get a buffer underrun, which is much harder to pull off. So actually, Windows Server 2003 is compiled with this option, as is Exchange and Office. And also, there's an option in Visual C++ 2003 to compile with what is known as safe exceptions, which means that when the code is compiled, we write into the PE header the list of all the valid exception addresses. So when an exception is raised, the OS checks in that list in the PE header, and if the exception address is not in that list, halt the process. This would have prevented code red. And so now, same again, but if we whack the buffer on the stack, the code just stops. But the cool thing is some of the sensitive data structures are not accessible now without getting a buffer underrun, which is much harder to pull off. High-level languages. Migrating to a high-level language where appropriate is absolutely the right thing to do. You'll see that in future versions of the OS, we'll migrate more and more code to managed code where it makes sense. You're not going to see a managed kernel any day soon. But certainly a lot of the management tools will move over to managed code. And a good example of this is actually in Windows Server 2003, the UDDI service is written in C#. Now, the best defense, by far, and this will help you mitigate attacks you don't even know about yet, is to reduce your attack surface. And to reduce your attack surface, you turn the feature off and you run with low privilege. But here are the steps that I go through. First of all, you review the code. Well, actually, there's step 0. You educate the people reviewing the code. Because if they don't know what to look for, have a guess how many bugs they're going to find? 0. Yep, I reviewed the code, no security bugs. It will be a little bit like me reviewing or doing a pre-flight inspection for a 747. Yeah, wheels are attached, wings are kind of droopy, must be full of fuel. Pointy bits of the back's pointing up, that's always a good sign. I'm sure the plane's ready to go. The day I'm down at SeaTac certifying 747's flight worthiness, I'll let you know. So you've got to train. So step 0 is train people. Step 1, review the code, find bugs, fix them. Even better, don't inject the code defects in the first place. Compile 3. Then you compile with the GS flag, just in case. Then you run the code as non-admin, just in case it is compromised. That way the code doesn't run as root or admin or system. The potential for damage is greatly reduced. And then finally, when you're done with all that, you turn the feature off. Use the 80-20 rule, or 90-10 rule, depending on how hardcore you are. But basically, if 80% of your population don't use that feature, you turn it off. It really is as simple as that. It's a very hard decision to make. And I'll tell you why. There are human emotions that come into that final decision. If you've got someone who has been laboring on some feature for 2 years, it is their little baby, and now you're telling them to turn the feature off. People don't like that. So you can't reduce the impact of the human element here. It's a very hard pill to swallow for some people. So there is no silver bullet. There is no one thing that this industry can do to build secure software. I wish there were, but there isn't. It's a whole series of things that you have to do. A series of remedies and a series of defenses. But the big one by far is process improvement. Changing the process so that it fosters people building secure software.